Okay. Um, your next homework assignment, number 5, is covering 2 topics, and so there's going to be a little bit more time to solve that one, combining both evaporation and infiltration. So it's due a week from Wednesday. I know it says that we're going to review the solution to quiz 2, but I haven't yet graded your quizzes, and I think it'll probably be best if I return the quiz and we go over the solution on the same day. So I'll give that back to you on Wednesday. We're going to begin section 3 of chapter 7 now. There's a couple of slides in the precipitation section of the course that we're not going to go through, and it's all interesting information, but probably less important than the stuff that we've covered already. So my suggestion is, of course, to learn the terminology that's in that list of terms that I gave you, and kind of the story of how precipitation forms, that chain of events that begins with warm, moist air rising through the atmosphere. I really concentrate on that, because being able to understand and explain that, I think, is important. All right, so in the hydrologic cycle, the evaporation of water from lakes and rivers and ponds is an important source of what is ultimately going to become precipitation. And so you've probably seen evaporation occurring before, like a puddle of water that dries up. And so what factors would you expect influences evaporation? Jeffrey?
Location.
In what way?
Well, if it's open, direct sunlight can hit without any impediment, that means it would evaporate more quickly.
Okay.
Or if it's heavily shaded.
All right. So more generally, it sounds like you're using location as a proxy for sun exposure. So, whether it's sunny, and I think you're absolutely right, that whether something's in direct contact with the sun versus shaded is going to have a big effect. What other factors can you think of that would influence evaporation?
Temperature.
Okay, temperature, good, for obvious reasons, yeah. Other things?
Climate.
Pardon me?
Climate.
Like, specifically what part of climate?
Like if it's very humid out.
Ah, humidity. Good, good, yeah. I think, boy, you've nailed the most important factors there. Let's watch a couple of videos just to set the stage for evaporation. The first of these is a time lapse that just shows a puddle drying, and let me wait for it. All right, so you can see that the evaporation is happening faster in the section that is in direct sunlight, and the closer it is to the direct sunlight. So here's the shade line, and so what evaporates first is not only what's in the direct sunlight, but what's closest to it. And if you think about the air that is transporting the water molecules away from the liquid, the air is going to be warmer as it's blowing over the surface. And so I don't know the direction of the wind in this case, but one of the things that we have to keep in mind is that the wind direction is also going to affect the evaporation rate. And so if the wind is coming from this area, which is warmer and drier, and it's going towards the liquid water, then it would be a different evaporation rate and a different evaporation pattern than if the wind was going an opposite direction. All right, in this next video, it's going to be showing the evaporation of water occurring very, very fast. This Leidenfrost effect happens when water is put down onto a skillet, and you've probably seen hot water dance around before, and it's vaporizing so quickly that the liquid water is kind of on a cushion of water vapor underneath it. So it's just moving all around, as the water is evaporating very quickly going into the vapor phase. It's kind of keeping the water droplets suspended. And so from that, we obviously see that heat plays a role in evaporation. And evaporation essentially is going from the liquid phase to the gas phase, and the latent heat of vaporization is the physical constant that describes how much energy it requires to go from liquid to vapor. Here's an interesting video that just shows when you've got extremely cold weather, how quickly a liquid can go into vapor. I think this is the one I'm remembering. They take some boiling water and throw it up into the air. I've done a similar thing to this here in West Virginia, but you can't do it as consistently as they can do it in Canada. In Yellowknife, it's -30. I don't think I've ever seen it that cold here. She's not wearing any gloves is the other crazy thing, but you notice she throws it and it just instantly goes into vapor. Alright, one last video. And I think we've seen this before in fluid mechanics. It's the idea that water can boil even when it's not hot. If this is the one I think it is, it's a vacuum bell. Alright, so when the pump is turned on and it starts to remove the air that is above the liquid, then the kinetic energy of the water molecules is enough that it can escape from the liquid phase into the vapor phase. The air pressure that's above it normally would be pushing down and resisting that liquid from going into the gas phase isn't there when the vacuum has removed all of the gaseous air above the liquid. So those videos kind of give us some ideas of some of the effects that are going to be accounted for in the numerical models that we have of evaporation. So this is a diagram that shows the wavelength of incoming radiation and outgoing radiation. And the light that comes in from the sun, incoming solar radiation, has a different wavelength than what's emitted from the Earth. And it's this incoming radiation that provides the energy to drive evaporation. And this is kind of a numerical balance that's showing of the energy that comes in, and here it's just done on a percentage basis. So it's saying of 100% of the incoming solar radiation, what percentage of it would be reflected by the atmosphere, reflected by clouds, reflected off the surface, and then of those incoming 100 units of radiation, 50 would be absorbed by either the ground or by the water. And then that 50 is all going to be emitted again, and then it shows of what's emitted, it may be as being absorbed by the atmosphere, going out, and this exchange of short wave radiation coming in and long wave radiation going out we can measure using something called a radiometer, which is a light meter that essentially you set out in the sun and it'll give you a characterization of how intense the solar radiation is. And a lot of the models that describe how quickly water will be evaporating require an estimate of the solar radiation. And so there are government databases that across the country have measured how much light there is. And then the long wave radiation is just estimated based on the temperature of the land, the temperature of the water. It's more not measured directly in very many places, but it's calculated based on the material and the temperature of the material. So the thing to remember is that incoming radiation is short wave and outgoing radiation is long wave. And I know that you've probably heard a lot about global warming, but global warming is an effect that, I believe that the climate is changing, but not in the short term. I mean, we're talking over decades and decades, the temperature maybe is increasing by a few degrees Celsius. This global energy balance, it's saying that the incoming radiation and the outgoing radiation is approximately equal, 100 units in, 100 units out. The effects having to do with climate change, the fact that, for example, the ice caps at the poles are shrinking, means that more water is going to be absorbing more energy, and glaciers that used to be covered with reflective white surfaces are now brown, and that absorbs more energy. I mean, that's going to very slowly change this balance, and so that more radiation is accumulating at the Earth's surface than is going out. But this 100 units in, 100 units out is true, over maybe a daily basis or even over several years, but it's over decades that we would have to look in order to not have that energy balance. This is an important factor that I kind of alluded to earlier in the semester, the idea that the radiation that's coming in from the sun is projected over a different area depending on the latitude on the Earth. And so in the equator, it's warmer in the equator, and there's more of that heating that causes the air circulation, because the radiation that's coming in is projected over a relatively small area, but because of the curvature of the Earth, the incoming solar radiation at the poles is distributed over a much larger surface area on the globe. And so that's why it's relatively cooler at the poles, and so the Hadley circulation, where there's rising air at the rising air at the equator and it's falling at the poles, is because of this effect. The other thing that is important about this, of course, as the Earth tilts about its axis through the annual cycle, then there's going to be relatively more and less solar radiation seasonally. And so when we're calculating evaporation rates, we're going to have estimates of the incoming solar radiation, and those estimates will vary seasonally, as well as the temperatures are going to be varying. So evaporation rate changes a lot over the course of a year. Here's a diagram that comes from your textbook, and it's just kind of, it illustrates not only does the radius of orbit of the Earth around the sun vary seasonally. You can see that at its closest is 146 million kilometers versus 151 kilometers at its furthest. But this is kind of showing how the amount of time that the poles are exposed to the sun varies seasonally as well. All right. Water exists only as a gas when the temperature is above 100 degrees Celsius, but sometimes the water vapor exists as a gas when the overall bulk temperature is below that. And it's when there have been successive collision of water molecules that give enough kinetic energy to one of those molecules to escape through the membrane at the surface and exist as a gas. And so just because the air temperature may be outside today, let's say, for instance, I think I saw is 47 degrees as I was driving in. So just because the overall average temperature is 47 degrees, that doesn't mean that all of the molecules in the atmosphere have the same kinetic energy that's associated with how much vibration and movement they'd have at 47 degrees Fahrenheit. There's a distribution of kinetic energies, kind of a normal distribution. And it's the sun's heat that keeps the water vapor as a gas, but here at the bottom, this is representing liquid water that's evaporating into the atmosphere, and it's the collision of those liquid molecules when one of them will finally have enough energy to escape and would be gaseous phase. And we can measure the quantity of gas above the water either by partial pressure. You probably remember that from chemistry, the measurement of partial pressure, where it's a percentage of the overall gas mixture. But we can also, when we're specifically talking about liquid, like water that's been evaporated, then relative humidity can be measuring the amount of liquid gas molecules above the liquid layer. The cause of the liquid vapor, the liquid going from water into the gas, is just some sort of energy being provided, whether it's boiling the water or sun shining on the liquid. And over the surface of the Earth, the overall average evaporation is 3 millimeters per day. And so that's going to be a lot more at the equator and a lot less at the poles. But then this temporal average also takes into account the evaporation over the land. And so there's a little bit of evaporation of soil moisture. And of course, transevaporation is a different effect, because it's having to do with how well the plants hold on to the water, as well as just the heat exchange. But this physical constant I mentioned before, the latent heat of vaporization, tells you how much energy is required to evaporate a certain volume of water. And so for a kilogram of water, you'd require 2.5 times 10 to the 6th joules, and there's a slight decrease in that depending on how high the temperature is, because you have to heat the water and then you have to do the phase change. And so we're going to use this constant in one of the methods for estimating evaporation rate, where we assume that the limiting factor is the amount of energy that's available. Here's a photo that I took a couple of years ago. It's driving on Route 2 towards Huntington, and this is the Ohio River. And you can see that there is a cloud that's formed just only above the river. It's clear skies on either side of that, but above the river we see a cloud. And so what do you know about cloud formations and precipitation, that effect that we've talked about before? Why would you suspect that the cloud is only above the river? I'll say, by the way, that this picture was taken in the fall. Any ideas? Why would the cloud only be above the river and no place else?
More moisture.
What's that?
More moisture.
More moisture, that's true. If you're right above the river, so it's a source of water. In the fall, temperatures change at a different rate. The land gets cool faster than water gets cold. And so the river temperature is just slightly warmer than the land that surrounds it, and warmer than the air. And so in the fall, not only is this a source of moisture, but it's also a source of heat. And so what's happening is that as the water evaporates from the river and it rises up, of course it's cooling, it's achieving saturation, and we have this temporary cloud. But then as the wind would push it to the side away from the river, then it immediately just dissipates, because the surrounding air doesn't have as much humidity as just immediately above the river. So this is just kind of an illustration that thermal effects are important when it comes to the evaporation of water and the formation of clouds. So remember that it's the incoming radiation and a kind of keeping track of what happens to it, and the exchange of shortwave radiation for long wave. And so long wave radiation is what's emitted. Like when you walk in front of a brick wall during the summertime and you can feel the heat coming off of that wall, that's long wave radiation. It's kind of a sensible heat. There's other radiation that goes back into space that's still shortwave because it wasn't absorbed by a surface. And so when radiation is reflected by air or clouds, or reflected off the surface rather than being absorbed by the surface, those can still be emitted shortwave radiation, but long wave is when the energy has been absorbed and it's heated up over the course of the day, and then in the evening is emitting that radiation back into the atmosphere. All right, so we're going to learn two methods for estimating the evaporation rate, and each of them considers the possibility that there is a limit on what's driving evaporation. And the first method, the energy balance method, just looks at the amount of solar radiation that's available, and the second method, the aerodynamic method, looks at the movement of air away from the surface where the evaporation occurs. So this energy balance method is asking the question, how much energy is there to drive the latent heat of vaporization? So that 2.5 times 10 to the 6th joules per kilogram of water, that energy has to come from somewhere. It comes from the sun. And so the energy balance method tries to estimate how much energy is coming from the sun and how long is it going to take to evaporate a certain amount of water. So the model is kind of conceived of this way. We have the control surface that the radiation is coming in through, the moisture is leaving out of, and it's enclosing in a control volume a certain amount of water. Now here the evaporation rate, E, is the rate that the height would be decreasing. And let's assume that there's no water coming back in, and so if you're going to be losing vapor out of the top, then the depth of the water would have to decrease. So the evaporation rate, E, is going to have units of length per time. And so remember, the average over the entire Earth is about 3 millimeters per day of evaporation. So that's the units that we'd like to estimate when we use this energy balance method, is how many millimeters per day would a pan of water go down if you set a pan out into the sun. And so the things that we'd have to keep track of to know that is we'd have to know how much heat is being emitted from the water and from the surface underneath the water. We need to know the radiation that's coming in from the sun. And here it says the net radiation, because what we're going to do is we're going to estimate how much energy is being reflected. We're going to try and estimate the effect of clouds and backscattering by the atmosphere. And then from that, you'll notice that the rate of vapor flow is going to be the density of the water, the evaporation rate, and then the surface area over which the evaporation occurs. And so water is going from the liquid phase into the gas phase, and so we're keeping track of two different densities, the density of the liquid water and the density of the water in the gas. And so here the Reynolds transport theorem is saying that the mass flow of vapor across this control surface is going to be the combination of the liquid water going down in the control volume. So the stored water is going to be decreasing its amount, and that's exactly the water that's coming out through the control surface. And so this density of the water times the velocity times the area, that's going to be the amount of moisture that we're losing. So if we assume that there isn't any loss of water off the bottom, if we just really want to simplify this and assume an impenetrable pan, then we can rearrange the Reynolds transport theorem and just say that the flow of gas through this control surface is how much the liquid level is going down. And so essentially that the mass flow of vapor through this control surface can be estimated by the evaporation rate, the surface area, and the density of the water. The specific humidity is an estimate of how much water is in the air relative to the mass of the air. And instead of expressing it as relative humidity is just how much water could be in the air versus how much is. The specific humidity is a little bit different because it's not changing as the temperature goes up and down in the same way that relative humidity is. The specific humidity is just an absolute ratio of the water to the overall mass of the air. And as the water vapor in the control volume, as the liquid level goes down, what we assume is that the humidity in the air above the water surface is constant. And so sometimes that's called the headspace. Headspace in environmental engineering terms means the gas that's above a storage tank, for example. So in a like at a filling station, at a gas station, there can be liquid gas, and then above the liquid layer there would be evaporated gasoline. And so, you know, it's important to know what's going on in the headspace, and the same thing is true here, where we assume that the humidity in the headspace is constant, and so as soon as it gets to this top layer, then it is just transferred into the air above it, and we assume 100% efficiency in transporting the moisture away. And that's one of the big simplifications of the energy balance method, is that we're assuming as long as there's enough sunshine to evaporate the water, then there's enough wind to blow it out of the way. And that's a real simplification, and probably what you've noticed before. We've talked about it, that you know, how you feel when it's really humid outside is different than how you feel if you're sweating in an arid environment. Like if you're in Arizona and it's 100 degrees, your skin feels differently than it might feel here and it's 100 degrees, because here you don't have perfect transport of all of your sweat into the gas phase. Whereas like in the desert example, you assume that if you sweat, it's going to evaporate rather than drip off. So one of the assumptions of this energy balance method is it's saying that the rate that the vapor is going away from this control volume only depends on how much radiation is available to evaporate. And it has nothing to do with the humidity of the air, has nothing to do with how windy it is. It's just all about keeping track of how bright is the sunlight and how much heat is that bringing to the water. So in that model, the evaporation rate depends on the specific humidity, which is, you know, the ratio of the air and the water, the velocity of the air that's exiting through the control surface, and here is where we would actually start to calculate in number terms the amount of heat that is available to drive the evaporation. In the latent heat of vaporization, if we know the temperature in Celsius, then we can find out how many joules are required to evaporate a kilogram of water. And the rate of heat input is the limiting factor that we assume. Now, we simplify that and just essentially will be given the net radiation flux, because that can be got from various websites. And in the homework assignment, what you're going to do is go to some radiation data for New Mexico, and over time the radiation data year by year over the course of the day is available, and it even takes into account how cloudy it was for a certain day, and you can estimate the sensible heat flux and the ground heat flux based on the temperature of the water, the temperature of the ground. That's the outgoing long wave radiation. And so back to the earlier theory, remember the incoming solar radiation is short wave, the outgoing radiation is long wave, and this is how we estimate the difference between the two, because the difference between the two is what's available to drive the evaporation. So the net radiation is going to be taking into account the scattering, and so this alpha factor gives you an idea of the angle of incidence and also the nature of the surface. You know, water reflects a certain amount of radiation. Different colors will have a different effect of how much radiation is scattered, and so the emitted radiation is based on the temperature. And in the end, this is how we estimate the evaporation rate. It's the net radiation that's available divided by the latent heat of vaporization and the density of water. Now, that's an old one. All right. So in this example, let's say that we have a measurement of how much energy is coming in from the sun, and this is at noon. And so over the course of the day, of course, the radiation would start at 0 in the morning, and it would go up to some peak, and then would taper down through the day. But if we wanted to find the peak evaporation in terms of millimeters per day, then what we can do is we can find the latent heat of vaporization with the given water temperature, and then calculate the net radiation, where the albedo, this alpha factor, takes into effect how much the radiation scatters off of the water surface. And then the amount of emitted radiation can be estimated by the temperature. And so let's just pause for a moment. I'd like you to get some practice using some of the information here, by the way, the stuff that's in red, isn't going to apply for this first example, but it will apply when we are doing the aerodynamic method a little bit later. So some of these factors aren't going to apply, but you basically are going to calculate the radiation emitted based on the temperature of the water, a couple of these constants, find the net radiation, and based on the temperature of the water, the latent heat of vaporization, and then what we'll get in the end by substituting in this E sub R formula is the evaporation rate in meters per day, millimeters per day. Okay, so there is 900 and what was the incident radiation? 978 watts per meter squared. So that's how much is coming in. A certain 35% of that is just reflected off of the water, and so it's not going to drive evaporation, the part that's reflected. And then the water itself is emitting long wave radiation to the tune of about 450 watts per meter squared. So that only leaves a net radiation available of 183.9 watts per meter squared. The latent heat of vaporization here, 2.4 times 10 to the 6 joules per kilogram. We put in the temperature of the air. Let's see, that's the water temperature. Hold on. Yeah, water temperature. Does it say that? Okay. You could use the density of 1,000 kilograms per cubic meter. This 996.3 is based on the temperature that the water's at. But the evaporation rate that you're going to get is 7.57 times 10 to the minus 8th meters per second. And then if we multiply that by 86,400 seconds per day and 1,000 millimeters per meter, then it should be about 6.5 millimeters per day. Now, keep in mind that that's just the evaporation rate when the radiation is this high point during the day, this noontime evaporation. And the radiation intensity is going to be starting at 0 and going up towards the maximum, and so the evaporation rate won't be this same evaporation rate through the entirety of the day. It would kind of peak at the noon and then go back down to 0, and so it's time, this is evaporation rate. So what we just estimated would be the peak evaporation rate. What we could do, though, is we could break it up into hourly sections, and we could find out how much radiation there is at each of these hours during the day, and then multiply the evaporation rate by the duration in between each of the measurements, and then find, instead of an evaporation rate, we could find an evaporation amount. So it would be a mistake for us to assume that it's going to be 24 hours of this, because for the first thing, the sun's not up 24 hours a day. But even if you knew that there's, say, 8 daylight hours or 12 daylight hours, it would be a mistake. It would be overestimating to multiply this by the total amount of daylight hours, because this represents the peak solar radiation in that example. All right, so when we get together on Wednesday, I'll have the quiz graded and we'll go over the solution. And then remember that this entire method is assuming that as long as the energy is available to drive the vaporization, that the air will accept the moisture. And that's a simplification that isn't necessarily true. So far what we've been assuming is that the air is able to accept as much evaporation as the sun is putting into it. And so the next look at it will we'll just address evaporation from the sense of how humid is the air and how far away is the moisture from being saturated. All right, that's it for today. I'll see you on Wednesday.